December 7, 1941. Pearl Harbor burns. Japanese dive bombers scream from the sky, sinking more Allied warships than any other Axis aircraft in history. But here's what they don't tell you about the engine that made it possible. The Mitsubishi Kinsei wasn't Japanese innovation. It was American technology, stolen, perfected, and turned against its creators. This is the shocking truth behind the engine that changed the Pacific War forever. The year is 1934, and Japan faces a terrifying reality. Their aircraft engines are primitive, unreliable death traps. While American and European powers soar ahead with cutting-edge designs, Japanese engineers struggle with engines that barely produce 400 horsepower. The Imperial Japanese Navy demands change, but innovation takes time Japan doesn't have. Enter Mitsubishi Heavy Industries and their audacious solution: industrial espionage disguised as legitimate business. They didn't need to invent a revolutionary engine from scratch, they needed to acquire one. The target was Pratt & Whitney's R-1690 Hornet, a proven American radial engine that had already conquered the skies. What happened next was corporate theft on an unprecedented scale. Under the guise of technology licensing, Mitsubishi gained access to every blueprint, every manufacturing technique, every hard-earned secret that Pratt & Whitney had developed over decades. American engineers, believing they were fostering international cooperation, handed over the very technology that would soon rain death on Pearl Harbor. The Kinsei project began as the A4, a direct copy of the 9-cylinder Hornet. But Mitsubishi's engineers weren't content with mere imitation. They doubled the cylinder count to 14, arranged in a twin-row configuration that would become their signature. The original Hornet's single row of cylinders produced respectable power, but 14 cylinders promised something revolutionary. By 1933, the engine underwent a complete redesign. Engineers reversed the cylinder head layout, moving exhaust ports to the rear. This seemingly minor change reduced back pressure and created cleaner installations, details that would prove crucial in combat. They increased compression ratios from a modest 5.3 to 1 to 6.0 to 1, extracting more power from every drop of fuel. The Japanese had taken American innovation and made it their own. What emerged was no longer a copy, it was a weapon. Inside the Kinsei's aluminum heart lay engineering that pushed 1930s technology to its absolute limits. We're talking about a 14-cylinder masterpiece that breathed fire at 32.4 liters of displacement, nearly twice the size of engines that had previously powered Japanese aircraft. This wasn't just bigger, it was fundamentally different. Each cylinder measured 140 millimeters in bore and 150 millimeters in stroke, precision machined to tolerances that Japanese industry had never attempted. The crankcase was split into 3 sections, each housing main bearings that supported a 3-piece crankshaft spinning at 2,500 revolutions per minute. Every component was calculated to extract maximum performance while maintaining the reliability that combat demanded. The supercharger was where engineering met desperation. A centrifugal compressor force-fed pressurized air into the engine, allowing it to maintain power even as aircraft climbed toward thin air. At sea level, early variants produced 730 horsepower. Push it to 20,000 feet, where air grew thin and cold, and it still delivered crushing power when pilots needed it most. But here's what made the Kinsei truly revolutionary: its power-to-weight ratio. At just over 1,200 pounds, it delivered nearly twice the power of previous Japanese engines while weighing only marginally more. This meant Japanese aircraft could carry heavier bomb loads, more ammunition, or simply fly faster and farther than ever before. The valve system employed pushrod actuation with 1 intake and 1 exhaust valve per cylinder. Oil circulation relied on a triple-section pump system, one pressure pump and two scavenge pumps, ensuring lubrication even during violent combat maneuvers. A planetary reduction gear with a 0.7-to-1 ratio translated the engine's high RPM into efficient propeller speeds. Yet for all this engineering brilliance, the Kinsei harbored a dark secret that would haunt Japanese aviation throughout the war. It was already obsolete before the first prototype roared to life. Behind the Kinsei's development lay one of history's most successful technology transfers, a 1937 arrangement between Mitsubishi and Pratt & Whitney that would reshape the Pacific War. While the world focused on rising tensions in Europe, American executives were quietly handing Japan the keys to aerial supremacy. The deal seemed innocent enough. Pratt & Whitney, flush with success from their radial engines, agreed to share advanced manufacturing techniques with Mitsubishi. American engineers, believing they were fostering peaceful technological exchange, provided detailed specifications, metallurgical knowledge, and production methods that had taken decades to perfect. What Pratt & Whitney's leadership couldn't foresee was how quickly their Japanese partners would weaponize this knowledge. Every tolerance, every alloy specification, every cooling passage design was studied, improved, and integrated into the Kinsei program. Japanese engineers didn't just copy American techniques, they enhanced them. The arrangement gave Mitsubishi access to advanced supercharger designs, sophisticated fuel injection systems, and metallurgical techniques that Japanese industry had never mastered. Within months, Kinsei prototypes were incorporating features that wouldn't appear in American engines for years. Direct fuel injection, turbo supercharging, and advanced cooling systems all traced their lineage to this fateful partnership. American aviation executives celebrated the deal as a triumph of international cooperation. They believed they were creating new markets while maintaining technological superiority through constant innovation. What they were actually doing was training their future enemies. The irony was devastating. By 1940, Kinsei-powered aircraft were outperforming American planes in Chinese skies. Japanese pilots flying aircraft powered by engines derived from American technology were systematically destroying Chinese Air Force units equipped with actual American planes. The students had become the masters. When Pearl Harbor's smoke cleared on December 7, 1941, American naval officers would discover their ships had been sunk by dive bombers powered by their own technology, perfected by Japanese engineers who had learned their craft in American factories. Dawn breaks over Oahu, December 7, 1941. In the pre-dawn darkness, 183 Japanese aircraft launch from carriers positioned 200 miles north of Pearl Harbor. Among them, 99 Aichi D-3A Val dive bombers carry the most devastating payload in naval history, 1,760-pound armor-piercing bombs capable of penetrating battleship decks. Powering each Val through the morning sky, a Mitsubishi Kinsei 44, producing 1,000 horsepower of pure destruction. The Kinsei's deep, unmistakable roar announced Japan's entry into World War II. As Val dive bombers screamed down at near-vertical angles, their engines howled with power that American defenders had never heard before. These weren't the underpowered, unreliable engines that intelligence reports had suggested. These were precision machines that maintained full power throughout violent combat maneuvers. Lieutenant Commander Kakuichi Takahashi led the first wave of dive bombers, his Kinsei 44 pulling him through a 70-degree dive toward the battleship Nevada. At 1,500 feet, he released his bomb and pulled out of the dive with G-forces that would have destroyed weaker engines. The Kinsei roared with approval, its 14 cylinders firing in perfect harmony as Nevada's magazine exploded in a towering fireball. Wave after wave of Kinsei-powered aircraft struck American ships with surgical precision. These engines didn't just deliver bombs, they delivered victory. The reliability that Japanese engineers had built into every cylinder, every bearing, every cooling passage proved itself in the crucible of combat. Not a single Kinsei engine failed during the attack. By day's end, Kinsei-powered Val dive bombers had sunk or severely damaged 8 battleships, 3 cruisers, and 4 destroyers. They had achieved what Japanese naval planners had only dreamed of: complete tactical surprise backed by technological superiority. The engines that had been born from American blueprints had just delivered the most devastating defeat in US naval history. The Pacific War had begun with American technology turned against American ships. But if you think the Kinsei's roar ended with victory at Pearl Harbor, wait until you hear the nightmare Japan faced when it came time to build them. By 1942, the Kinsei's combat success had created an impossible demand. Every Japanese aircraft manufacturer wanted these engines, but Mitsubishi faced a production crisis that threatened to strangle Japan's air war before it truly began. Building precision aircraft engines required materials, machinery, and expertise that Japan simply didn't possess in sufficient quantities. The first challenge was metallurgy. Kinsei engines demanded high-grade aluminum alloys, specialty steels, and exotic materials that Japan had previously imported from the very nations they were now fighting. Substitutions were attempted, but inferior materials led to catastrophic failures. Pistons cracked under combat stress. Bearings disintegrated during high-power operations. Entire engines seized at the worst possible moments. Machine tools presented an even greater challenge. German Junkers had provided some equipment through technology transfers, but Japan lacked the precision manufacturing capability to mass-produce engines to the tolerances that combat demanded. Quality control suffered as production ramped up. Engines that had performed flawlessly in prototype testing began failing in operational units. Skilled labor became critically scarce as the war expanded. Experienced machinists were drafted into military service, replaced by hastily trained workers who struggled with the precision that aircraft engines demanded. Manufacturing defects increased exponentially. Engine overhaul intervals shortened dramatically. Pilots began reporting power losses, overheating, and complete engine failures at rates that would have been unthinkable in peacetime. The numbers tell the story. Mitsubishi managed to produce approximately 12,000 Kinsei engines throughout the war. Impressive for Japanese industry, but insufficient for their expanding air force. Compare this to American production. Pratt & Whitney alone manufactured over 150,000 engines during the same period. Japan was fighting a technological war with industrial-age production capabilities. By 1943, strategic bombing of Japanese factories made the situation desperate. Key suppliers were destroyed, forcing engineers to redesign components around available materials. Quality suffered further as factories were dispersed to avoid bombing, breaking up manufacturing teams that had worked together for years. As Allied technology leaped forward in 1944, Japanese engineers faced a terrifying reality. Their masterpiece was becoming obsolete. American fighters like the F-6F Hellcat and P-51 Mustang were powered by engines producing 2,000-plus horsepower. The Kinsei, still limited to approximately 1,300 horsepower in its latest variants, could no longer compete. Desperate innovation led to the Kinsei 60 series, Japan's last hope for technological parity. Engineers introduced direct fuel injection, a revolutionary system that precisely metered fuel into each cylinder. Turbo supercharging followed, forcing even more air into the combustion chambers. Compression ratios climbed to 7.0 to 1, extracting every possible horsepower from the basic design. The Kinsei 62 represented the engine's ultimate evolution, 1,560 horsepower of pure desperation engineering. This monster required a complete redesign of aircraft that carried it. Cowlings grew massive to accommodate enlarged air intakes. Propeller spinners doubled in size. The engine's signature roar deepened to a thunderous growl that announced its power from miles away. But evolution came too late. The A-6M80 fighter, powered by the Kinsei 62, completed only 2 prototypes before Japan's surrender. The engine that might have restored Japanese air superiority never reached combat units. Material shortages, bombing damage, and industrial chaos had finally overcome Japanese engineering ingenuity. Even more heartbreaking was the story of advanced variants that never left the drawing board. The Ha-43, an 18-cylinder monster designed to produce 2,200 horsepower, represented everything Japanese engineers had learned about high-performance aviation power plants. It incorporated features that wouldn't appear in American engines for years, but Japan's industrial collapse made production impossible. The final Kinsei engines rolled off production lines in August 1945, just days before Japan's surrender. They were magnificent machines, technological marvels that showcased Japanese engineering at its peak. They were also relics of a war that industrial capacity, not just innovation, would ultimately decide. And just when it seemed the Kinsei might rise again with unstoppable power, history pulled the plug in the most dramatic way imaginable. When the guns fell silent in August 1945, the Kinsei's legacy was written in both triumph and tragedy. This engine had powered some of the most successful aircraft in aviation history, yet it had also demonstrated the limitations of brilliant engineering when facing overwhelming industrial capacity. The combat record speaks for itself. Kinsei-powered aircraft had sunk more Allied warships than any other Axis power plant. From Pearl Harbor to the Solomon Islands, from the Dutch East Indies to the Philippines, the engine's distinctive roar had announced Japanese air power at its zenith. Pilots who flew Kinsei-powered aircraft spoke of reliability that bordered on supernatural, engines that brought them home despite battle damage that should have been fatal. But the Kinsei's most important legacy wasn't military, it was technological. Japanese engineers had taken American concepts and pushed them beyond what their creators thought possible. Direct fuel injection, advanced supercharging, and sophisticated cooling systems all traced their development to Kinsei research programs. Many innovations wouldn't appear in Western engines until years later. The engine's development history revealed uncomfortable truths about technology transfer and international cooperation. The 1937 Pratt & Whitney arrangement had seemed like enlightened business practice, sharing knowledge to advance human flight. Instead, it had armed Japan for the Pacific War. The lesson was clear: technology has no nationality, and today's peaceful partner might become tomorrow's enemy. American intelligence officers who studied captured Kinsei engines were shocked by their sophistication. These weren't crude copies of Western designs. They were genuinely innovative power plants that had evolved beyond their American inspiration. Post-war technical reports recommended immediate adoption of several Japanese innovations into American engine programs. Perhaps most remarkably, the Kinsei had achieved its greatest successes while operating under impossible constraints. Material shortages, production difficulties, and constant design changes had plagued the program from beginning to end. Yet Japanese engineers had consistently delivered combat-ready engines that outperformed their specifications. It was engineering excellence triumphing over industrial limitations until those limitations finally proved insurmountable. The Mitsubishi Kinsei proves that technological superiority means nothing without industrial capacity to support it. Japanese engineers created a masterpiece that dominated early Pacific War skies, but American production lines ultimately determined victory. Today's military planners still study this engine's development, seeking lessons about innovation, espionage, and the dangerous consequences of technology transfer. To explore more crazy engines history, make sure to watch our next video.